Hey guys, we're here to talk about absolute dating, right? Which can be a little tricky of a concept. All right, so just bear with me on this. Definitely make sure you know your math, fraction math, and percentage. That's going to be key here to understanding this. Okay, so elements are chemical substances made up of one type of atom, and one element can have several forms. Okay, so there isn't just hydrogen or carbon, all right? There might be different versions of them based on certain particles in there, all right? So let's look at these. So differences in varieties are caused by differences in the number of the neutrons in the nucleus. So if you remember, there's protons, neutrons, and electrons, which are subatomic particles within an element. So neutrons can vary a little bit depending on the substance. Okay, and when a substance has more or less neutrons than the normal form, it's called an isotope. Okay, and these isotopes are not stable forms of the element. Okay, so carbon-14 is an example of a radioactive isotope. Carbon-12 is the normal neutral version of it. And if you count up, 1, 2, 3, 4, 5, 6 protons, and both of them have 6 protons, all right, because they're both carbon, but the neutrons are what differ. So there's 1, 2, 3, 4, 5, 6 neutrons here. There's 1, 2, 3, 4, 5, 6, 7, 8 neutrons in carbon-14. Okay, so that's the only difference between the two, but because of these extra neutrons, this becomes a little unstable, and we'll talk about what happens and what we're able to do with this now. Okay, so isotopes are unstable. It's radioactive. It emits hazardous particles and electromagnetic energy until it becomes stable. Okay, so that's what the decay process is all about. So this process is called radioactive decay. So carbon-14 is a radioactive substance that wants to go back to its stable form or a new stable form, in this case. So what happens, gives off energy, and it becomes a stable form, which is nitrogen-14. So we call this the parent, the carbon-14, and this is the daughter that it turns into. Okay, and the daughter, you're going to notice 1, 2, 3, 4, 5, 6, 7 neutrons now. So it got rid of a neutron, and 1, 2, 3, 4, 5, 6, 7. So there's 7 protons. So it actually gained a proton in the process. Okay, so sometimes it will lose certain subatomic particles, sometimes it will gain certain subatomic particles, depending on what type of decay is going on. You'll go over that more in chemistry, but what we have to know is parent, daughter. Okay, and we have a pairing on the reference table that you'll be able to look those up. Okay, so a single atom of radioactive isotope decays randomly. However, because there are billions of atoms in a sample, they'll decay at a predictable rate that we can actually figure out the age of the material by looking at that. Okay, so this is what we call half-life. So on the reference table, you'll find this on page 1. Okay, so the radioactive isotopes are listed here. So carbon-14, potassium-40, uranium-238, and rubidium-87. Disintegration tells, again, the parent and what it changes into, its daughter. Okay, you'll note that potassium-40 has 2 daughters, argon and calcium-40. Okay, uranium-238 is Pb206, which is lead-206, and rubidium-87 turns into strontium-87. Okay, now the half-life is the time it takes for half of the material to decay. Okay, so you're going to say, why half? Well, this is something we can measure, we can compare. So they decide to use fractions, starting with a half first, and then a half of a half, which is a quarter, etc. All right, so we'll look at how that works in a moment. Okay, carbon is 5.7 times 10 to the 3 years. Same thing as saying 5,700 years. So know those interchangeably. Potassium 40 is 1.3 billion years, okay, or 1,300,000,000 years, okay. Uranium 238 is 4.5 billion years, okay, or 4,500,000,000. And rubidium 87 is 49 billion years. Okay, so big number on that one. All right, so let's see how this works and how you actually use it. Okay, so the half-life is the time it takes for one half of the atoms in the radioactive isotope to decay or change to its stable isotope form. Each radioactive isotope is going to have its own individual half-life, like you saw on the chart before. The half-life cannot be changed. It's unaffected by any external factors like temperature or pressure, so that's why it's a good measurement, good thing to use. Okay, there is a video which I'll put the link up for this. You guys can look at that video and take a look, and it's definitely a good one. Explains this and shows some visuals on it. Okay, now, so how does half-lives work? Okay, so obviously this is 100% radioactive to start. Okay, so you're going to notice they have 1 there because the whole number is 1. Okay, after the first half-life, half of this material is going to decay, and the other half is still going to be radioactive. Okay, so obviously we could put numbers to this, so if we know the half-life and we see this fraction of radioactive material left, we can know that that's the age of that material. And then same thing for the next half-life. So second half-life, 3/4 have decayed now, because you add on the original, and 1/4 now is unchanged or still radioactive, right? Because this turns, this basically halves again, which half of a half is 1/4. Okay, and obviously the other half is going to be decayed, so this bar gets bigger by that other half. Okay, so that's the way that works. And then continuing on, so the third half-life, now 7/8 have decayed, leaving 1/8 of the original atoms unchanged or still radioactive. And this halving will keep going on indefinitely until a point where you can't read the fractions anymore, because there has to be a point where it's not usable anymore, or you can't read enough of the atoms to be able to get a measurement on it. And that's where using the right isotope is important. Okay, so comparing the amount of undecayed substance to the amount of decayed substance, carbon-14 has a relatively short half-life, so it's good at dating organic remains or ones that are 50,000 years old or less. We also call them recent fossils, so you'll hear them differently in different questions. Other radioactive isotopes have longer half-lives, like uranium-238, are going to be more useful in dating older rocks, millions and billions of years old, because again, the half-life is so long, so it's probably a better measurement because you still have enough of the radioactive atoms to be able to measure it and get an accurate number. Whereas carbon-14, you wouldn't, right? Because it would be such a minuscule amount left over after this 50,000 years have expired. Okay, so again, picking the appropriate half-life to match the age of the substance approximately is important. Okay, so let's see how this works. So if we take carbon-14, how many years in one half-life? All you simply do this over at the board here. The half-life of carbon-14 is 5,700 years. Okay, so let me just write that for you. All right, or 5.7 times 10 to the 3 years. You want to deal with exponents. Sometimes you have to deal with the exponents because they'll give it to you that way in the problem. You can do the same technique though that I'm doing. If you're doing half-lives, 2 half-lives, you're going to go 2 times 5,700. Okay, and if you do that in the calculator, That is 11,400 years. Okay, and then 3 times 5,700 in the calculator, and you should get 17,100 years. Okay, and you can keep going on and on. Sometimes they go out to 6 half-lives. You just do 6 times 5,700, etc. Okay, uranium-238, on the other hand, is 4.5 billion years. Okay, that's 1 half-life. The same thing as saying times 10 to the 9 years. Just remember 10 to the 9 is a billion. That's an important factor to know. Obviously, you're just going to double this number, so this would be 9 billion years, which you guys know the age of the Earth and solar system from the reference table is only around 4.6 billion years. So you're not going to be going beyond that number, really, of 1 half-life for uranium-238. Okay, so how does this work? So if we take carbon-14, okay, as our radioactive substance, okay, if we measure, again, a fraction of 50% or 1/2, make sure you know fraction and percentage, that would tell me that the fossil is 5,700 years old, okay? If there's 1/4 radioactive or 25% radioactive still, the fossil then is 11,400 years, because you go 2 times 5,700 for 2 half-lives. Okay, so just remember the fraction that matches up to the half-life number, okay, and same thing with the percentage. All right, and I sometimes will just do a list and then go down half, quarter, eighth, and then 1 half-life, 2 half-lives, 3 half-lives. I'll make a little like chart out of it. Okay, so 3 half-lives, 1/8 or 12.5% is 17,100 years. Okay, we can also do this graphically. So here's an example with a graph. You can read simply off the graph sometimes in the questions. Okay, so let's do these. You could pause the video and actually try these on your own first. Okay, so here we go. So letter A, how many years and 2 half-lives you use radium? Well, 2 things you could do. They already gave you that half-life is this. So all you have to do is go 2 times 1620. All right, and that will give you the answer. Or look for the fraction that corresponds to 2 half-lives, which is 1/4. And your answer is this one here. So the answer is 3240 years. 3,240 years. Okay, B, how much undecayed material will be left over after 4,860 years? All right, so undecayed, remember, versus decayed is a difference. So undecayed would be the radioactive amount that's left over. So in this case, it would be 1/8. Okay, or if you want to do percentages, that would be 12.5%. Okay, so make sure you know both, because in different questions they're going to give you either one. Okay, so how many years for 4 half-lives? So all you do is the same thing. You could do 4 times 1620. Okay, and it's 6,480 years. Or technically you could take this number, the 4,860, and you could add the 1620, and that will give you the same answer. So there you go. All right, so either way, it works. Okay, whatever you're more comfortable doing, so 4 times 1620, that's what I did. And then lastly, 1/4 of the material is left over. How many years have gone by? So once again, just looking off the graph, you can get that answer, so 3,240 years. Okay, and we'll look at some other examples of this moving forward, definitely more difficult ones. But this is a good start to get you guys used to this. And if you have any questions in class, make sure you guys definitely ask, because this can be a little tricky and difficult for some students. All right, thank you guys for tuning in. I'll see you next time.